Expert tunneler Brendan Riley knew how central the TBMs were to the dig.
Basically, the machine is a mini factory. The factory is provided with power, it's provided with water, it's provided with electric, it's a workshop of the machine, preventive repairs. Basically, it's self-contained. It's got everything.
12 French and British TBMs excavated the tunnels 24 hours a day, 7 days a week. The TBM's high-tensile forged steel blades carved out 10 tons of rock with every turn. The biggest machines cost £10 million each, but as they've been specially designed for this one job, at the end they would simply be scrapped. The race between French and British tunnellers would be won or lost by their TBM's rate of progress. The Brits had the fastest machines, devouring up to 75 metres and 36,000 tonnes of rock a day. The French machines were 25% slower, but did have a key advantage. Their cutting heads were protected by a waterproof housing that allowed them to work on safely, even through waterlogged soil. 1 month into the tunnel dig, with the ground staying dry, the speedier British TBMs began to get ahead. Every day, hundreds of concrete slabs were shipped in to line the tunnel roof as it was dug. They were as big as a family car and 3 times as heavy. This is no ordinary concrete. Specially made to a recipe using granite, it's stronger than the stuff they use to build nuclear reactors. The TBM's powerful hydraulic arms pushed the slabs into place, forming the tunnel wall. The TBMs had to be kept supplied with slabs and constantly moving forward. British Chief Engineer Crichton knew that the schedule was tight. And with the tunnel's £1.3 billion budget all put up by private finance, government bailout was not an option. With the dig costing £1 million a day, each hour's overrun would add £40,000. By January 1988, the Anglo-French tunnelling race was hotting up. But the Brits were holding on to their lead. The rivalry underground is keeping the dig on schedule, but speed isn't everything. Success relies on keeping both tunnels precisely on target. If they stray off course, lives could be at risk. It's enough to daunt the boldest of engineers. The Channel Tunnel Project, the longest undersea tunnel in the world. 2 rival teams of French and British workers were each digging out from their own shoreline. The plan, to meet midway under the English Channel. The tunnellers' goal was to win the race for the midpoint. But what kept the engineers awake at night was much more fundamental. The fear that the 2 tunnels wouldn't meet up. If the 2 tunnels missed each other, that would mean last-minute course corrections, which could create sharp bends. And the high-speed trains that would use the tunnel had to have a broadly straight course to operate safely. The margin for error was frighteningly slim. The tunnels could not deviate by more than 2.5 metres. Being off target was not an option. But lives were at stake too. If the massive tunnel-boring machines strayed off course, they could hit waterlogged ground. The result could be disastrous. Flooding, or worse, tunnel collapse. It was imperative that the TBMs were guided along a safe and accurate route. That meant conducting one of the world's longest and most in-depth underground surveys. Rewind to August 1986, 18 months before tunnelling began. When surveyor Eric Radcliffe took on the job of plotting the tunnel's course, he knew the scale of the challenge he faced.
France you can see over there, that's the French coast. So we had all that way to drive the tunnel and keep it online for that 38 kilometres. Actually, from here it doesn't look too bad, but it's a long, long way.
Plotting an accurate course over such a long distance underground is a surveyor's nightmare. In tunnels, the normal rules of surveying don't apply. Surveyors normally work by measuring a series of angles at control points along the route. It's all a matter of geometry. Above ground, with 360-degree visibility, plotting a course is relatively simple. Eric Radcliffe explains the difference.
The whole road is opened to the air. All the survey control points from which you do the setting out are already established over the whole length.
Underground, there are obvious complications. All the surveyors can see is a wall of rock. They can't see ahead to plot the course. Roads have one other plus point over tunnels. Because they're flat strips on the landscape, they can only go off course in two directions: left or right. A tunnel occupies a three-dimensional space underground. It can go off course not only left or right, but also up or down. The two halves of the Channel Tunnel had 4 potential ways to miss meeting up. It's like asking a golfer to sink a hole-in-one blindfolded from 34 kilometres. To keep the tunnel on course and on target, the surveyors had to use a secret weapon: geology. Along its underground route, the tunnel would be driven through a layer cake of different soil and rock types with very different consistencies. The geologists needed one stratum that went right across the channel. This stratum would provide a trail to help keep the British and the French tunnellers on course. But it must be exactly the right type of rock for tunnelling. Jean-Luc Desaisnes was one of the geophysicists charged with tracing the perfect stratum for the tunnel to follow. On the French side of the channel, Desaisnes began his search. It would have to be waterproof to resist flooding, and compact enough so it wouldn't collapse during the dig. In these cliffs, Desaisnes found his prize. Water poured over this seam of rock without soaking in, evidence that it was waterproof.
The soft rock, impervious, so no water in the tunnel. This is a perfect situation for boring a tunnel.
It's called blue chalk. But it was one thing to identify the ideal rock, another to discover its course. Geologists drilled a series of boreholes into the seabed and dropped probes that fired sound waves deep underground. The aim, to measure changes of speed in the sound waves as they passed through different rock and soil layers. It sounds straightforward, but it wasn't. Tracing the course of the blue chalk meant sinking 12 of these boreholes right across the channel. A tricky task in one of the world's busiest sea lanes.
You have a high traffic of vessels. You have a tide, you have waves, so it's a difficult place for making accurate investigations.
The geologists concluded the blue chalk would provide a feasible route across the channel. If they were wrong and the TBMs left the waterproof strata, they could hit waterlogged ground. with devastating consequences, flooding or even tunnel collapse. Spring 1988, 3 months into the Channel Tunnel dig. The tunnellers were gouging their way through the rock deeper and deeper underground. Standing between the tunnellers and the risk of flood was the TBM's laser guidance system. Laser guidance is commonly used to keep above-ground structures like roads on course, but underground it had to be used in a more imaginative way. Instead of looking ahead to see where they were going, the tunnellers looked back to where they'd been. Laser beams continually scanned backwards to the tunnel's start point to compare it with the TBM's changing location.